Time is 11 a.m. Let's begin here. So assignment number 4, we will start discussing that today. It is due Friday, April 3rd. Also, these presentations are coming up in about 1 month. If you have not finalized the topic with me yet, you should within the next 1 to 2 weeks, so that hopefully over spring break you can spend some time preparing for it. Today we will finish up parallel processing and we will start high performance computing. Are there any questions? Okay, we left off last time about page 23 in the notes. And we were talking about, as I mentioned at the very beginning of parallel processing, or about the beginning, that there are basically 2 packages that we're going to be talking about in this class to do parallel processing. One is called the parallel package. That's one that we focused on so far. And the other one's the foreach package, which we will start discussing shortly. If you remember with parallel, and also this is true with foreach too, the way it basically works is that your main R session itself, when you ask R to do some parallel processing, it will actually open up additional R sessions or instances, you could say, in the background to do your computations for you. So if you ask to use 2 cores, it will open up 2 more R instances that run separately on each core. Now there are some side effects to doing that. First of all, let's say that you're doing some kind of Monte Carlo simulation and R gives you a warning message. If you remember with the BCA intervals, when we ran everything on one core in the main R session for these Monte Carlo simulations, when we were doing a confidence interval for sigma squared, there was some warning messages about how you're at the extreme points, or you're close to the extreme in terms of the number of resampled values and what ordered value you're picking off from those. Well, since R is running some of this stuff in the background, all the warning messages are printed in the background, and you don't get to see them. Okay? Because essentially they're printed on these other R sessions. And once those R sessions are closed, okay, they're gone. Any kind of warning messages. So because of that, you got to be a little bit careful when you do parallel processing in R. You want to, test out everything and feel confident that everything's going to work well without you having to worry about potential warnings that may occur and what those consequences are. Okay. Now, the second thing that you have to be concerned about is that, oftentimes when you're running a computer program that's going to take a while to run, you realize after you push, you start to run, you realize, oh shoot, I did something wrong. I want to stop it. So in R, what do you typically do? Well, you hit the escape button, or what you could also do is click on the miss there and then stop all computations. Okay, RStudio has some similar things that you can select as well. Well, you could do that. Let's say if you're doing some parallel processing, you could do that, and you'll come back to a command prompt. The problem is it doesn't actually stop everything that's going on. While you're able to get back to the command prompt, remember you have these separate R sessions running in the background. Those will still keep on running. And they will run until they would normally reach their conclusion, which obviously may not necessarily be ideal, because what happens, for example, if you decide that, okay, you fixed the problem, then you're going to run some more Monte Carlo simulations doing parallel processing. Well, now some of your cores are taking up running the old stuff that you don't want running anymore. So how can you stop the other stuff from running? Well, you might be thinking, well, what you could do, if you remember from last time, what you could do is, where is it? Right there. issue the stop cluster command or function in your main R session itself. And that should close everything out. It won't in this case. So what can you do? Well, you're going to have to actually go to the task manager itself. Find your R instances that are running and then force them to stop there. That's the only way that I know of that you can get this to stop running. Are there any questions? Okay, let's move on then to using the foreach package to do the parallel processing. Now, as I said last time, actually the foreach package is easier to do parallel processing, a little bit easier than the parallel package. But I want to focus, I do want to always talk about the parallel package because it's in the main implementation of R rather than the foreach package is something that's contributed, in this case by Revolution Analytics. So since it is contributed, you're going to have to download it and install it. When you install it, you also get another package called, actually no, I don't think you get this other package, if I remember right. On page 26 I mentioned this, there's another package called do parallel, which the foreach package uses. I think foreach will not automatically install do parallel, but you know, you can try it on your own, you can see if it works, okay? If it doesn't install, well, just install it yourself. Now there's a nice vignette that talks about how to use foreach. There's the address for it. Now the foreach package has one really main function called foreach. And it operates very similarly to the for function. That's what makes this easier to use. So this is how you can do it. Foreach, I'm sorry, let me back up a second. No, that's fine, we can do this one. So foreach, and then just like with the for function, you say I equal 1 to R. Let's say if we have capital R different, maybe Monte Carlo simulations that we're running. And then you have some additional arguments that are optional. One is called .combine. And this allows you to specify how you want the results that are coming back from the separate cores, how you want them to be combined into one format. So let's say that you are maybe using 2 cores, and the final results on each core is a matrix. Well, you probably will want, if in terms of a Monte Carlo simulation, you probably want to combine these matrices together. So what could you do there? Put R bind. So combine by row. You know, last time when we did the parallel package, we had results returned to us in terms of a list. So if your results were returned to you in terms of a list here from each core, what you could do to what you could do to combine the two is to do some similar stuff like we did last time. You could use the list function. Maybe your stuff is just a vector that's coming back to you from each core. Well, how could you combine different vectors from different cores? Well, use the C function. There's another argument there that can be very useful called .package. This is explained on page 26. Well, let's say that the stuff that you're doing on each core requires you to actually load some kind of package, like maybe the boot package. Well, just because, again, you have the boot package loaded in your main R console, it's not loaded in these new R sessions that have opened up. So you actually have to tell R to open up these other packages again. And so you could say .package equal, let me make sure I get the syntax right, quote, boot, end quote. That's how you could do it. You'll see an example of that shortly.
You just like put that comma after,
yeah.
Comma .package after the .combine.
Yep, yeah, and if you had multiple packages that you needed, you'll use the C function to combine these, essentially these character strings that contain the package names. Okay, now I haven't really seen this before anywhere else in R. Almost reminds me of a SAS macro. Now next, the syntax, you need to say percent do par. So do parallel the following. And then inside your brackets, you basically have code like you would normally with a for loop. So let's say if you're trying to save the results into a matrix, for example, you can say save bracket I comma n bracket so that the ith row of that save matrix contains your results. So that's just the general syntax then that's involved here with the for each function.
We need 2% for do par.
Excuse me?
Do we need 2% signs or just one?
Just one.
Okay.
And do note that, let's say if up here, and I'll show you how to do this in a second. Let's say up here you've set up, let's say you want 2 cores. For each automatically splits it up into the 2 cores. It does all that automatically. Okay, so let's take a look at a result, or I'm sorry, an example that does this. And if anything wasn't clear before, I think it will be clear after taking a look at this example. So we're going to continue with these Monte Carlo simulations involving 6 confidence intervals for sigma squared. To do it in R, we say first of all library for each, and also then library do parallel. These packages automatically also load the parallel package too. And so these packages rely on actually using some functions from the parallel package. In particular, make cluster. Just like what we had with the parallel package. This basically tells R again, hey, I'm going to use 2 cores in this particular instance. Then, this is from the do parallel package, you have to say register do parallel, and then the results for make cluster you put inside there. So I can then next time how long everything takes, so I say I use proc.time, and then again I can use the cluster set RNG stream function to enable separate streams of seed numbers to be used for each core. And then lastly, then I do the for each function. So I say for each I equal 1 to 500 simulated data sets. I'm going to combine the results in the end using rbind. I need to also load the boot package for each core, or each separate R session on each core. And then I say do par. And then simply, I have a function called sim.func. And this sim.func function contains all of my code that calculates the intervals for every single data set. Previously, we had simulated our data. We had put it into an object called y.sim. And notice here how I have an I there, meaning that the ith data set is going to be going into sim.func. Let's take a look at what sim.func looks like. This is not in the notes because it was actually in previous notes. Where is it now? There we go. Here's my sim.func. This is essentially the same function that we were using in the bootstrap section when we were doing the Monte Carlo simulations. This calculates my 6 different intervals. Also note that, when I use the bootstrap here, of course, I need a calc.t function, and also since I'm using the jackknife, I need a calc.t2 function as well. One of the key differences between parallel and using the for each package is that this was actually defined already in my program itself. I did not need to define it inside of my for each call, which was essentially different from what we had with the parallel package. Remember with the parallel package, I'll go back up. So I used the par lapply to actually do the main calculations. I had to have a function called per.core2 that contained everything that was going to be sent to each core. And so per.core2 contains similar code to what we just saw, where basically what I did, I read in some information that contained my code, like the calc.t function, for example. So an advantage then to using the foreach function is a little bit less, I think, clunky. That here I've already defined this in my original program itself, and then I can call that function that I've already defined in my program. That function actually calls another function or actually two other functions that I've defined in my program already. I did not need to necessarily really send that out to each new R session. So that is an advantage of using foreach. Yes.
So for the do part, we do need a percent before and after.
Oh, I'm sorry. Maybe that's what you were talking about? Okay. Yes, you do.
Okay.
Sorry about that. Let me just double check that. And the code works, so I would assume.
Assuming it's right in your code.
Yeah. Yep. You do need percent before. Thank you. Okay. So let me come back over to my program here. Oops, wrong one. So at the end, I still use stop cluster to close out these extra R sessions. And again, this will work as long as you don't do anything like I talked about at the beginning of class, where you try to stop all the computations. And then check how long it took, 6.8 minutes. This is a little bit longer than what it did with the parallel package. I believe the parallel package took 6.6 minutes. Yeah. And this is what I have generally always found, that for each function is typically just a little bit longer it takes. But not so much that you would be worried about using it, or you would think about not using it, generally speaking. And so now my save.all2. Let's take a look at what save.all2 means. So let me come back up here to my code. What is it? So look at save.all2 got the results from foreach. Oh, I need to do that. Save.toAll got the results from foreach. So that means all the stuff that was calculated with sim.func went into save.all2. And if we look at sim.func, notice how the results are returned for every single iteration, essentially as a vector. And all this stuff was put together then using the rbind function. Okay. So then I just use my summarize function that actually comes from the Bootstrap notes, just to summarize all the calculations, and we just get what we've essentially gotten before. Any questions? So you can see it is relatively easy. Okay, then some final comments overall. Just through my investigations of foreach, I've only used it now for a little over 2 years. I've seen some people talk about how there's supposedly a lot of time spent with the combination of the results in the end. Meaning that if you have, let's say, lots and lots of cores you're using, so that you have to combine lots and lots of results in the end, things can get slowed down. I noticed that when I was using a 3rd generation processor, but now that I have a 4th generation processor, I haven't noticed that at all. I'm not for sure exactly why, but I haven't. But I decided to leave the bullet in there still. And the second bullet here I think we've kind of talked about before, but I think it's worth emphasizing. And that is, if you want to use your computer simultaneously while you're doing parallel processing, make sure you don't use all the cores for the parallel processing. So let's say you have a 6-core computer, like I have on my my desktop computer in my office. You know, I would not use all, if I was using that desktop computer, I would not use all 6 cores if I still wanted to use the computer to do other stuff. Instead, what I would do is at least leave 1, maybe 2 cores open so that I could do my own work, and then the other 4 or 5 cores are doing the parallel processing for me. And the reason is that, again, if you're using all cores, well, you can't do anything else on your computer because your computer's resources are essentially tied up to doing the computations. The parallel package does have other useful functions that can be used as well to do some of the parallel processing, although I have not had really success at least trying to use that one. Okay, so that concludes the parallel processing section. Are there any questions? Okay, let's get into then the high performance computing. Oh, I'm sorry, let's actually talk about the assignment. And I had it open, and for some reason I closed it. I don't want that one. Just a second. Okay. So, purpose of this assignment is simply to give you some experience using parallel processing. That's problem number 1. Problem number 2 does high performance computing. And after you see us getting started the high performance computing section, you're going to see how it's just basically parallel processing taken to a different level. And all you're going to be doing is duplicating some of the results that you've done before, but now in a parallel processing context. So the main thing that we're interested in is, well, how much faster can stuff be done that you've already done before? So that's why I wanted to make sure that in assignment number 2, when you were finding the true confidence levels for the correlation coefficient, I wanted to make sure it took some time to complete the calculations because I knew we were going to investigate those calculations again in the parallel processing section. But to keep it a little bit easier for you, we're just going to do the n = 20 simulations again, not necessarily the n = 100 simulations, which some of you were concerned about with it taking so much time. So, for these same simulations, change some stuff here. First of all, I guess this isn't even simulation related. For your computer that you're using for this assignment, I want you to tell me the operating system that you have, type of processor, the processor speed, memory, number of cores, and number of threads that are available to you. So very similar to what I did at the very beginning of the parallel processing notes. So I want to know about your computer. Part B, simulate the data exactly as what was done in my answer key. So if you simulated it differently, don't use that. Use what was in my answer key for assignment number 2 to simulate the data. I want everyone to have exactly the same data. Then part C, write a function that calculates then the 6 intervals that were in assignment number 2. If you remember, there was 2 essentially asymptotic base and then 4 bootstrap base intervals. Write one function that can calculate all of them for a data set. As a check, make sure that your asymptotic interval without the transformation ends up being that. Then part D, complete the table below using the foreach package that we just discussed and with the function that you just wrote in part C. What I want you to do is record the time in minutes that it took to complete the simulations through using 1 thread of a processor, 2 threads of a processor, and then the max for your computer, max number of threads. Also along the way, please tell me what the estimated true confidence level and estimated expected lengths are. So again, you kind of have an idea if your answers are correct because you can compare these these estimates here to what were in the answer key for assignment number 2. Then, while 2 threads are used on your computer, provide proof that indeed 2 threads are being used. And we looked at ways that you could examine, maybe like stuff in the task manager that showed you that indeed, yes, 2 threads are being used on the computer. I want a screen capture of your computer that proves to me that indeed you are using parallel processing and doing this stuff correctly.
Sorry, I missed it. For 1C, do you want us to write some other function, or do we just use the symbol?
Actually, I don't remember exactly what the function was. Maybe it was the exact same one. Well, without looking at assignment number 2 answer key, I don't know if my function is exactly the same. Maybe it is.
Well, my question is of course, for the one that's given in the notes is different because it's of variance, and this one will be for correlation. But
well, I mean, obviously you can't use the same function as what was in the notes.
Right. So,
but I'm thinking in terms of the answer key previously. Sorry, I guess I just don't remember off the top of my head. I wrote this assignment a few weeks ago, and I don't remember. What I recommend that you do is take full advantage of the resources that are available to you in the previous assignment.
Okay.
So maybe I've made your life easier without knowing that.
Maybe those 2 points are like extra points.
Yeah, kind of. So that is the first problem of the assignment. Are there any other questions? Robert.
If we're working in groups, do you want just one, the information about one computer?
Just one.
Okay.
Okay. Any other questions? So, while we haven't talked about high performance computing yet, basically problem number 2 is doing the same, a lot of the same stuff that you did for problem number 1, but now you're going to be using the supercomputers on campus to do it, and you're going to be using the parallel package instead of the foreach package. And so you can see that you have a very similar table to what we just saw. Since there's a lot of cores that are available to you on the supercomputers, having you go up to 10 cores. And just record the time, and then in the end you're going to use a plot to show me what happened over the different number of cores that you had, similar to what was in the notes. Okay, so that's assignment number 4. Let's now talk about the next section, high performance computing.
Will you be coming back to this assignment, or?
Probably not, because I think it would be pretty self-explanatory.
So for part D, do you want it for each of the intervals, or do you just want it?
Yeah, it has nothing to do with intervals. It's just how long is everything taking.
It's number of threads and time, right?
Yeah.
Oh, okay. Yeah, that's fine. Thank you. Sorry.
So let's talk about high performance computing. So, about 4 years ago, maybe 5 years ago, I was having some research problems I was having my students work on, and I told them, and the calculations they were doing was take some time, and I told them that you really should investigate the supercomputers that are available to you on campus, because I think you could really have some benefits to using that than trying to do the simulations in our department and the various student computers that are around. There wasn't even a simulation computer available in our department at that time. And my students ignored me a few times. And so eventually I got to a point, okay, I want to figure this stuff out on my own. So I think it was about 2012 I started investigating this myself. And then I discovered wow, this is really cool. I wish I would have known about these resources that are available to us on this campus, because if I'm ever going to do a large set of Monte Carlo simulations again, or anything that takes a long period of time, I'm not going to try to use any computer that's in our department. I'm not going to try to use my own computer. I'm just going to simply put it on the supercomputers because it will run faster. And so that's why I think it's important that we definitely talk about this in this kind of a class. And so when you use these supercomputers, you're doing essentially what's called high performance computing. And what high performance computing, or HPC for short, basically means is that you're using parallel processing in supercomputers to get a job done, like a computer program, as quickly as possible. And the way that these supercomputers actually work is essentially, you can imagine, let's say, a whole bunch, maybe all these computers here are tied together in some very high-speed communication network. And to take advantage of having all these computers hooked up together, what you have to do is use parallel processing. So the supercomputers that you will see shortly are essentially a whole bunch of Intel or AMD processors, just like what might be in our own computers, just networked together with a very fast connection. And if you want to take advantage of the supercomputing capabilities, you have to use parallel processing to do it. I think, before I started looking into supercomputers and exactly what makes them fast, I guess I didn't necessarily understand that aspect that these supercomputers are essentially using almost regular old processors, Intel or AMD processors, like you can buy. It's just there's a whole bunch of them, and they're all networked together in a way to make everything fast. Okay, so the supercomputers that we have available to us are at the Holland Computing Center. The HCC controls the supercomputers for the University of Nebraska system. So it's not just Lincoln, it's Omaha, Kearney, and the Med Center. There are 2 locations for the Holland Computing Center. The location here on this campus is the Shore Center, which is the old athletic department offices that are just south of the Memorial Stadium. They're kind of actually underneath the stands a little bit there. And so that's where it's located on this campus, and as you will find out shortly, you might have to actually visit there to do something in order to do the assignment. And then the other location is the Peter Keywood Institute on UNO's South Campus. Here's the supercomputers that are available to us at HCC. The 2 that we are going to use are the 2 fastest. One is called Crane. Crane became operational just over a year ago. And the other one's Tusker. And Tusker came operational maybe about 3 years ago. And so let's take a look at the specs for them. Also, I should mention that Crane and Tusker are actually on UNO's campus. They're not here. But you won't even notice that, because the way that you're going to operate or use Crane and Tusker is essentially through your own personal computer. You'll have some log information that you can use to log on to those computers, and even though that there's 60 miles between the 2 campuses, you will not notice any kind of communication delay at all. Okay, so Crane. Crane is a 452 node computer. What that basically means is you can think of a node as a computer itself. So essentially there's 452 computers that are networked together. Each of these nodes has 2 CPUs, 2 regular old processors. They are Intel Xeon E5 2670s that run at 2.6 gigahertz apiece. These processors each have 8 cores. So there are 16 cores per node. So again, my computer here has 2 cores, 1 processor. But each of those nodes up there have 2 processors, each with 8 cores. So there's 16 cores per node. The memory available on each node is 64 gigabytes. That's a lot. The connection that allows the nodes to communicate is something called a QDR InfiniBand. I really know not too much about it other than it's fast. And the storage that's available. So in total, there's 1,452 terabytes that are available for storage. where 1.8 terabytes are available per node. So that's a lot. Then Tusker, it's 106 nodes. It uses AMD Optitron 6272 processors. Each node has 4 of these. And each of those processors has 16 cores. So there are 64 cores per node. That's going to be advantageous to us when we want to do parallel processing versus the 16 cores per node. And you'll see why as we go along in this section. It has more memory per node, 256 gigabytes, and it has less storage overall. Now the other 2 computers that are available at the Holland Computing Center are Sandhills and Red. I have not used those at all, and they are actually located on this campus. We won't use them. Okay, so Crane is often referred to as a computing cluster. Tusker is often referred to as a computing cluster. The reason why the word cluster is used often with supercomputers is that essentially you have clusters of these processors together. That's why, groups of these processors. So that's why it's called, sometimes you even hear people call it cluster computing. So let's see here. So some more information about these supercomputers. Tusker, how fast is it? Well, it runs at 40 teraflops. So what is it? What I mean by that? It can do 40 trillion simple calculations like x plus y per second. Okay. Well, how does that compare though to the world's fastest computers? So when I was first looking into supercomputers, the fastest computer was called Titan. Titan is now number 2, so that's why I haven't really updated these notes. And so every 6 months, new rankings of these supercomputers come out. And so when I first wrote up these notes, I had to use the November 2012 rankings. And here's information about Titan. You can take a look at their web address to find out more about it. And this is what Titan has. 299,008 Optitron cores. Okay, so let's compare that to what Tusker has. And I should have even said this before. So Tusker has 64 cores per node. So if I take 64 times the number of nodes, I think it was 106, we get 6,784 cores. So it has a lot more cores to it. Let's do Crane. Crane has 452 nodes, each with 16 cores, 7,232 cores. So I guess that's why it's the second fastest in the world. But on each node, it also has a NVIDIA Tesla K20 GPU. Now we've talked about GPUs a little bit when we were talking about presentations here. You know, GPUs are graphical processing units. They control how graphics essentially are displayed. And GPUs are becoming more and more useful in terms of doing, let's say, regular old computations, not just necessary for graphics. And so each of these nodes has a GPU available to it as well. Titan runs at 17.6 petaflops, or 17,600 trillion calculations per second. Again, Tusker did 40 trillion. Yeah. So you can see it's a lot faster. There was a nice National Public Radio segment on Titan a few years ago. You can take a look at that if you're interested. As of the latest rankings for the world's supercomputers, Titan is the second fastest, as I mentioned before. The fastest supercomputer, and this has been this way now for about a year, is one that's based in China. It has 3,120,000 cores to it, and it can do 33.9 petaflops. So it's a little bit faster than Titan. And since I've been keeping track of this stuff, I decided just to kind of leave this table in my notes and and continue updating it. So when I was first looking at the table, this was early 2013, the November 2012 rankings were out. The speed of the 500th fastest computer, these rankings only go 1 to 500, was 76.4 teraflops. So you can see that Tusker was about half as fast as the 500th fastest computer. And you can see over time what has happened. The 500th fastest computer now is 153.4 teraflops. So it's doubled in speed. The federal government has recently announced back in November that it's going to put some more funds into doing even a faster supercomputer that's supposed to come out in 2018. Unfortunately, I don't remember exactly how fast it's supposed to be. Let's take a quick look. So it's going to be called Summit. Both Titan and Summit are at the Oak Ridge National Laboratory, which is in Tennessee. Let's see now. So it's going to have, I thought I had, maybe I'm just not, does it say anything about the teraflops? Oh, 5 times faster than Titan. So, now we're talking about, what was Titan again? 17.6, so now we're talking about almost getting up to 100 petaflops. Okay, so with respect to Crane, when it first was operational, would have just made the top 500. It was running at 121.8 teraflops, and this was the part of the actual email that announced Crane to everyone. It says, for example, this is 3 times the machine that Tusker is. But Tusker does still have some advantages, in particular the number of cores per node. Well, how does this all compare to my own computers? So I was curious about that. So my desktop computer that's in my office, well, it's a few years old, it's probably still my fastest overall. Again, each core runs at 3.2 gigahertz, and I have 6 cores. It's an AMD processor. I wasn't able to find, through some Google searches exactly how fast it is in terms of flops, but a very similar processor runs at 57.7 gigaflops. So let's compare that to Tusker. My computer is 0.0014 as fast as Tusker, and 0.0000033 as fast as Titan. So that gives it, put it in perspective. But again, for emphasis here, these speed advantages occur only through using parallel processing. So, if you want to use, let's say, Tusker or Crane, and you just use one processor, it's just going to run as fast as a regular old desktop computer. And for those who are new to supercomputing, that's often something that they don't necessarily realize. That you have to use parallel processing to take advantage of the speed, the advantages of speed. Okay, so that was a brief introduction to HPC and HCC. Let's talk about HTC, high throughput computing. This is something that's a little bit different from high performance computing. We're not going to talk about HTC much, but I do want to mention it because sometimes they're talked about in other outlets at the same time. So what HTC is concerned about is that you have a lot of calculations that need to be done, and you just want to get them done. You're not necessarily as concerned about speed, but you have lots of calculations that need to be done, and you want to somehow find a way to get them done. And HTC applications are often done on independent computers to do the computations. So for example, maybe I might use my computer here, or maybe I might use a computer that's located in Argentina. And through what's called the Open Science Grid, a whole bunch of supercomputers are all linked together around the world. And you have a way to, let's say, submit an R program to it. And through its scheduling system that's available on the Open Science Grid, it might send some of your computations out to Argentina to run. And then when that computer is maybe needed for something else, it will change and maybe send the computers to send the computations up here to UNL to Red, that supercomputer. And then later on, it might send the computations out to Australia to do the computations. That's what high throughput computing represents. I also have some other additional information about high performance computing there too. You can take a look at. In particular, one that's kind of interesting. So iPad 2s run at 1.5 to 1.65 gigaflops, and that corresponds to the fastest computer that was in 1985. For those of you who have an iPad, you might find that interesting. Okay. So, page 9. You will need to get an account from the Holland Computing Center to run Tusker and to run Crane. If you click on this website here, oops. Okay, so I've given you a web address to start the process of getting an account. The first thing that you have to do is select a research group. Now, you will see me listed here under Builder. Do not select that. Do not. Instead, select one called Stat Tools. This is what I had set up for my Tools for Statisticians classes the last 2 years. While it's a different name than our class here, we can still use it. This is just a separate research group that I have set up. So select the Stat Tools. Select a username that you want to use and click Submit. Now after that, to be honest, I'm not 100% sure exactly what happens. The reason being is because there have been some security break-ins to the supercomputers here, and new mechanisms have been come into place to make it more difficult for people to get accounts and to actually log on to these computers. So what I think will happen is that an email will be sent to the Holland Computing Center, and then Holland Computing Center will set up an account for you. Then they'll say, you need to come down here in person to the Shore Center and finish up some stuff. I think that will happen. At least that's what happened last spring. I don't know if they have changed some stuff so that you no longer actually have to be there in person. Okay?
They just like check ID or?
They might check your ID, and you're going to see another aspect too of how you log on, that why they need you to be there. Okay?
If we already have an account, should we somehow affiliate that with?
If you already have an account, that's fine. You can use it.
Okay.
Now, after the semester is done, I will delete all of you, or I will have all of you deleted from the Stat Tools account. So this will only be active during the semester. Okay. So now to log on to Crane and Tusker, you simply use your own computer here, and you use a number of different programs that are available to you to actually log on to the computer. And essentially the interface that you will have is very similar to the command prompt in Windows. So let me just show you the command prompt here. So I just right click, this is again Windows 8.1. I just right click on the Windows symbol and come to the command prompt. And here's my command prompt. And before Windows existed, there was the disk operating system created by Microsoft called DOS, and this essentially allows you to work with your computer like you would have with DOS. So 20 plus years ago, when I first started using a Microsoft, let's say, base computer, this is how I interface with my computer. And there's various commands such as dir that allows you to see your directory structure. Now, you need to be able to come up with this command prompt way to interact with Tusker and Crane. One way to do that is to use a program called Putty. So do you use Putty?
I've never used Putty.
Okay, what do you use?
I just SSH with the to the command line and on my Mac.
Okay. Well, maybe you can show it to me sometime. This is what at least they recommend for Windows users, the Holland Computing Center, so this is what I've used. It would be nice if there was something better. For people who have only worked in Windows-based environments, this might seem kind of archaic, because what you're going to have to do is actually type commands. There's not going to be windows that pop up. And so this program called PuTTY allows you to type commands to Tusker or Crane. And the program's free. You can download it from this web address. And simply what it is you download an executable file, and all you do is you just click on the executable file on your Windows-based computer, and it runs. You don't install the program like you would with pretty much all the other programs that are out there. So, let me see here. So I'm going to, I have a little link down here to PuTTY, so I'm going to open it up. And I know it's small, but I can't make it bigger. You can at least look on page 10 to see what it looks like. And so I'm going to log on to Tusker. And so I have some logins that have been set up for Tusker and Crane. The way that you log on to Tusker is essentially use the address tusker.unl.edu, Crane's crane.unl.edu. And you can simply put this in here for the host name. Since I've done this a number of times, I've saved my actual settings here. And if I just double click on Tusker down there, I come to a login. My login happens to be Builder. And then ask for my password. Don't look. Actually, nothing pops up. And all your keystrokes are hidden. And then it comes to this following information. Again, it might be small, but you can see it on page 11. So one of the things that they've implemented over the last year to do break-ins to the due to hackers getting into the supercomputers here is that they have now a two-step authentication process to make sure that indeed it is you who's logging in. And you have three options of how you can log in here. One is called the dual push, which basically sends to an app on my smartphone my login information and expects me to verify that indeed it is correct. You might have run into two authentication processes in other places. So for example, I think Facebook and Google, they have it set up to do some kind of a second authentication where it will send something to your smartphone to verify that indeed it is you. So number one here is, again, you can download a free app on your smartphone, and if I hit one there, it will Tusker will essentially send something to my phone, and I can hit a button on my computer that says, okay, it is me. I'm going to demonstrate, and that's what I demonstrate on page 12. Instead, what I'm going to do is demonstrate number 2 there on my smartphone, and basically I'll get a phone call. And so I'm going to hit 2. It's going to take a little bit. Yes, this is one time when it's okay to have your phone on in a classroom situation. And I got a phone call here. I know you can't hear it, but indeed it is ringing. And it asked me to basically hit some kind of key on my keypad. And it doesn't matter which one you do. I'm just going to hit a key and it says, thank you. And now, no, we'll try it again. Maybe I wasn't doing it fast enough. I was talking too much and I wasn't doing it fast enough. Okay, we'll just close that out. Oops, wrong program. I don't want that program right now. Not yet. Come on. There we go. So eventually, when you do it right, it says, thank you, goodbye. And now I am logged on to Tusker. And you can see where I'm logged in here, it's like a command prompt, similar to what we saw in Windows command prompt interface. And at this $ here, I can type commands. We'll look at these commands shortly, but if you remember the ls command, that's in R to view everything that's in your R workspace. If I type ls here, guess what? I have a directory listing. A lot of the functions that are in R get its names from using Linux. This is a Linux-based operating system here. So we'll talk about the details of using that maybe a little bit later today. Okay, so now I have a way to interact with Tusker. I can type certain commands that will allow me to run R programs, for example, from the command prompt. You will not have an R console window. You will not have like a graphics window that popped up. Everything is going to be run in what's called batch mode. You'll see that shortly. Okay, now let's say that I have, well, let me back up a second. So we're not going to actually, let's say, type our programs directly on Tusker or Crane. Instead, what we're going to do is type our programs on our own personal computers that we have, and then we need to transfer those computers to Crane or Tusker. In other words, we need to upload them. We're going to use what's called FTP to do that, File Transfer Protocol. And there's another program that allows you to use FTP. This is the one that's, again, recommended by the Holland Computing Center, called WinSCP. Do you use WinSCP by chance? Well, you wouldn't use Win. Never mind. But do you use FTP at all?
I use SCP.
Well, yeah. I forget exactly what SCP stands for. Something like Secure Connection Protocol.
Yeah.
And basically, I guess I started using FTP about 20 years ago, File Transfer Protocol, and there are more secure ways to do it. And so it's an FTP program, but it uses more secure connections. Anyway, okay. So WinSCP is a free program. You can download it at that website there. In fact, this is the program that I use to interact with the web server on campus. So all my websites that are stored on an INR web server, and for me to transfer files back and forth between the web server and my own personal computer, I use WinSCP to do it. Okay, so let me open up WinSCP. I have a little icon down here that allows me to open up. Now this is an actual program that needs to be actually installed on your computer, so it's a little bit different from PuTTY. But we see various addresses that I can use to log on. So for example, if I look at Tusker here and I click on Edit, you see the host name tusker.uno.edu, just like what we saw with PuTTY. So since I've done this a number of times, I've actually saved my login information so I don't need to retype it every single time. So I'm going to have, there's my username builder. My password's already entered there as well. I'm going to log in. Oops, nope. Let me try this again. Okay. So I'll ask for my password. Again, this is more due to over the last year due to the security break-ins. That's why you actually have to retype it again. I forgot about that. And again, it asks me, well, for my second authentication to make sure that I am who I am, I'm going to do 2 for a phone call. And eventually, I have the phone call. It asks me just to simply type any key in my keyboard or keypad, and there I am logged on. And so now you can see my directory structure in a little bit more of a, probably more familiar format for all of you, where it's actually kind of in a Windows-based format here. And so for example, if I click on Comp Stats, a folder that I've made up for myself, and here is then assignment number 4. The answers right there. I'm not going to show that to you. But you can see some other stuff that other files that I've written as well. And all like the .r files are my programs. How did I actually get the programs onto Tusker itself? So this is actually Tusker right here. How did I get there? All I did was, maybe I just click and drag over and drop it in there. It will automatically transfer. Let's see, do I want to do that? No. I'll just do it with this program to show you what happens. It transfers it. That's it. Now if I see it right there, and if I want to delete it, just hit the delete key on my computer. I have some other options available too that are pretty self-explanatory of how you can interact with your files there. You can create new folders rather easily by, for example, create directory. So this right-hand portion of this WinSCP window is Tusker. The reason why I know that is you see the folders up here. You see Lustre, that corresponds to the type of storage system. I'm in my work folder. You'll learn more about that shortly. My research group is Builder. My login is Builder. So I just happen to have a login and a work group that's called exactly the same thing. So for you, it will be Lustre work, stat tools, and then whatever you've chosen for your username. On the left-hand side here, you see the folder structure of my own computer itself. I typically don't worry about that on the left-hand side there because you can just, like I said, simply drag and drop stuff back and forth. So if I wanted to, let's say, move this save.txt over to my Windows computer, I just drag and drop it. I'm not going to do that though. Okay, are there any questions? Let's close this out. Okay. So page 16 then. There is another way too that you can log on to these computers in terms of the second authentication step. I'm not for sure if this is the right name for it. It's called, I think, a YubiKey. Basically, it's a thing that will plug into the USB port on your computer, and that will allow you to do another kind of authentication. I have a YubiKey. Fortunately, I never got it to work, so I've never really used it. I'm fine with my phone. But if, let's say, you don't have easy access to a phone to use for, the option number 1 or number 2, you can request one of those YubiKeys, and you can say, please charge it to the Department of Statistics. Okay. The key is that because it costs like $5 or $10 to get it, the key point that I'm trying to make about the key is that you will need to return it at the end of the semester. Otherwise, you will owe us the money for the YubiKey. Okay.
If we have a phone that's not a smartphone, we can just do the phone call part, and that's.
I think you can still do it. I think you can still do it.
The
And I
first
think that
option is an actual app.
is an actual app, yeah. And I think that's one of the reasons too, to where you probably will have to go down to the Shore Center because they want to set those aspects up. So so I got this phone in, I think, November, and on my previous smartphone I always use option number 1. For some reason now that with this new phone I can't get option number 1 to work, the app to work, and I just haven't had the time to go down to the Shore Center to do it because the phone call works just fine too.
There's the SMS option too, so that should work too.
Excuse me?
Number 3 is SMS, so that should work too.
Well, that third option, I thought the third option was the.
SMS.
I thought. Well, I guess I don't even know what
It's
SMS.
just an SMS text message.
Oh, okay.
So like a
Yeah.
regular phone.
Ah.
So
So
that
it
should
should
work
work
with
for-
any phones.
Okay.
Yeah.
I guess maybe when I was updating this, I wasn't paying attention to that aspect because I was thinking the third option was the YubiKey, but I obviously wasn't paying attention to what the third one said.
Yes, that
So-
one would just be a text message.
Okay. No, thank you for bringing that up. Now there are other programs that you can use to interface with Tusker and Crane. I have been using also Tunneler, if that's how you pronounce it, I'm not for sure exactly, which basically combine PuTTY and WinSCP into one program. since they've implemented some of these new security protocols, I haven't been able to get it to work. Okay, so again, to interact with Tusker and Crane, you are using a Linux-based operating system. How many of you have used Linux? So just one. Okay, two. Good. So to give you a little bit of background about my experience with it, so my department of statistics, when I was in grad school, I kind of said this to you before, we had about 10 or 15 Unix workstations all around the department that the faculty used. We also had some central servers as well that were Unix-based. And the way that the students interacted with it was that they could use essentially dummy terminals that were set up in our own computing lab, and that's how I used the computing system there for my first 4 years of grad school. Then I bought my own Windows-based computer, and I was able to do something similar to PuTTY to interact with the computers. Once I graduated and got done with some research afterwards, I basically didn't use Unix or Linux for about 10 years. Then when I came back to using the supercomputers here, I said, oh, it's Unix, Linux. I hadn't done that for a while, and fortunately, after a few weeks, everything started coming back to me about how to actually use it. But Unix and Linux is basically the operating system that scientists use to do hardcore science, and so it's good for you to get some background in it instead of just using simply a Windows-based computer. And so what I'm going to do is talk about give you enough background in Linux so that you can run our programs and have a little bit of idea of what's going on in the background, and so that you can do some simple commands if needed, like how to get help. You're not going to be an expert in Linux. I don't think you really need to be as a statistician, to be honest. Just so you know the basics of how to operate this. So first of all, what's the difference between Unix and Linux? There is actually a difference. Unix is actually essentially was a proprietary operating system, and then Linux came along as a free clone. And so what we are actually using is Linux. Now, to interact with the operating system, you have to use what's called a shell. And basically, this is just like the command interface in Windows. So, just like this. And using then PuTTY, we are in a shell right now. There are a number of different shells that you can use with Linux-based operating systems. We are using one called Bash, called Born Again Shell, after the person who created it, Born. If you want to know more information about using it, there's some websites. Okay, so the most basic thing that you can do then once you log in is to get a directory structure. And, oh shoot, I should have done this before class. Let me change some settings here. Make my font bigger. Unfortunately, off the top of my head, since I haven't done this for a year, having to make my font bigger, I don't remember exactly how to do it. Oh, there we go. Oh, let's do 14. Let's see how that works. I was going through my lecture last night at home. Of course, I didn't have to worry about font size because I could see exactly what was on my computer. So, how is this? Is this big enough? Okay. So we've already done the ls command, which essentially is kind of short for list. List everything out. And that's how you can see all the files that are stored in the default directory that you log into. Now, also with each of these commands that you can do at the prompt, there are various options. And for most of the cases, to do the options, you have to do the command name space, then a dash, And then often it's just a single letter that corresponds to a particular option. So if I do -L, I get a little bit more of a comprehensive listing of the files that are on, or in my default folder or directory that I have logged into. Now let's say that you want to see, well, what other options are available to you for ls? Well, that's where you can go to the help. The way that you access the help, you use the command man for manual. So if I do man ls, I get into the help for ls. Now if you thought that R's help was rather terse and hard to understand, well, man is even worse. But if you want to page down, you just hit page down. If you want to page up, you can page up. If you want to do one line at a time, you simply hit the space key. And so if I page up to where it says -L, so you can see -L here, it says use a long listing format. And often at the end, you get some additional information as well, similar to what you would with the help for R. Remember that R and then, I guess, previously S, originated on Linux-based operating systems. So that's why you will see some similarities between how R does stuff, as does how Linux does stuff. So if I want to exit out of here, I can hit escape. Nope.
Q.
Q, thank you. Q, or you can do a Control-Z. So if you ever are having problems in Linux, you can't get out of something, hit Control-Z. It will take you back to the command prompt. Okay, so well, what directory am I in right now? So if I do pwd, I can see where I'm located in the file system, essentially, on Tusker. In the home directory, builder research group, builder login. That's where I'm located right now. Let's say I want to change what directory I'm in. So if you notice here, I have a directory called compstat. Suppose I want to go in that. So to change directory, I say cd for change directory, compstat. If I do ls, I don't have any files in this particular version of my compstat directory. If I want to go back to where I was before, I say simply cd ... And notice I am back where I was before. If I want to, let's say, jump to a whole new folder, and if I happen to know the address of it, I'm going to jump to, this is the very bottom, page 20, I'm going to jump to the work folder. This is actually where you will need to type or run all your R programs in. Work, stat tools, builder. And so if I do ls there, now you can see some stuff that I have in my corresponding folder there. On the top of page 21, and also I guess I should say, if I want to just do pwd again, that gives me my position of my work directory, or the directory that I'm working in right now, I should say it that way. Work, stat tools, builder. Now, if you look on page 21, and we'll probably end it with this, you see a nice little diagram that kind of shows the directory folder system on Tusker and also Crane. It's set up exactly the same way. When you log in, by default, you will go right here in the directory structure. Again, home, group name, username. So that's where I have logged in. Home, builder, builder. Up here you have a root directory that connects you, essentially connects home to work. So you can use cd, or there would be other ways to do this as well, that allow you to get to the work folder, I should call it directory. It's a better way to do it in Linux. Work directory, your group, your research group name, and then your username. This is where you need to run all your programs. So one of the first things that you should do whenever you log on to Tusker or Crane is to cd your way over to here. One quick way to do this is mentioned on page 22, is to use CD $work, and that will take you to where you need to go. Okay, are there any questions? Okay, we will continue with this introduction to Linux next time. That's it for today.